In Chapter 6, we're going to be taking a look at the study of a topic called differential equations. And in 6.1, we're going to be solving differential equations. So the good news about 6.1 is we've actually already studied this topic before. Back in 4.1, towards the end of that lesson, we saw that one question could ask us to solve a differential equation, which is really just another way of saying to solve or to find a particular solution. So the good news is all a differential equation is, as you can see in this picture here, is just an equation with a derivative in it. And again, we've seen those equations since Chapter 2, but more specifically in Chapter 4 and 4.1, we started to solve those differential equations, which again was just another way of saying to find a particular solution. Okay, so just like I said a moment ago, a differential equation is just an equation that has a derivative in it. So here we have dy dx, the derivative of y with respect to x is equal to e to the x. And that, of course, is a differential equation because it has a derivative in it. We know that a general solution represents every possible solution. So again, if you took the time to look back at 4.1, at the end of 4.1, we solved two problems. One was worded for you to solve for a particular solution. The other problem said to solve the differential equation, which again was just another way of saying to find a particular solution. So if you want to find a particular solution, you would first need the general solution, which is the equation that has that plus c in it. And then to find a particular solution, we would be required to have a point or some sort of initial condition so that we could plug in that point to find the c value. And you can see here y is equal to e to the x, and there is no number at the end of it, so I guess in this case the plus c was equal to 0. But of course, that c could be any value depending on the point that we're given. So let's go ahead and kind of go through the process of solving that differential equation that we see above. We have the differential equation dy dx is equal to e to the x, and we're given the point 0, 2, and we want to find y, which would just be another way of saying to solve the differential equation, or again, to find a particular solution. To find that particular solution, we need a point, so we can plug it in to find that plus c. That point quite often is called an initial condition. So if you were look back to 4.1 and look at the steps of finding a particular solution, or if you just happen to remember them, you need to first put your equation into its differential form. In other words, move the dx to the other side. Once you do that, we can integrate both sides. The integral of 1 dy is just y. The integral of e to the x with respect to x is e to the x, and don't forget the plus c. So you saw this way back in Chapter 4 and 4.1 again, where I can graph a bunch of these particular solutions. In one case, maybe the c is equal to 0. In another case, maybe the c is equal to 1, or 2, or -1. And we would have these graphs here. And just as a reminder, there's an infinite amount of solutions to this differential equation until we're given a point so that we can find that plus c. When we graph all these solutions visually, we call those solution curves because they're the family of curves that represent the general solution of our differential equation. But if we want to find that particular graph or that particular solution to our differential equation, we need to plug in the point that we were given. And in this case, we're given the point 0, 2. So if we plug that into our differential equation, e to the 0 is 1. If we subtract 1, we find our c value is 1. So our particular solution in this case is e to the x plus 1. So it happens to be that graph second from the top. That particular solution, again, is only good, so to speak, for that one initial condition of 0, 2. As soon as we use another point, it would be a different particular solution. One other thing that kind of comes up with these differential equations, and we're really not going to see it much, if at all, in this course, but I definitely want to go over this idea, is the order of a differential equation. All the order of a differential equation is just the highest derivative you see in your particular differential equation. So if we take that example we've been using and talking about so far, you'll notice that the derivative we see in this equation is a first derivative, so we would call that a first order differential equation. In maybe some more advanced classes where you might be dealing with higher order derivatives, maybe this would matter a little bit more, but in this next example, you'll notice that the highest derivative we see in this particular differential equation is a third derivative. So we would say that this is a third order differential equation. Again, not something we're really going to use much, if at all, in this class, but definitely something that could be brought up at later points in calculus. Okay, so something to realize about this topic we're about to embark upon is that there are entire courses dedicated to solving differential equations. Usually after Calculus 3, you'll take a course called Differential Equations, and you'll really get into solving some very complicated differential equations. So I suppose there's some good news here. While those classes will cover much more difficult differential equations, we're going to focus on what are called separable differential equations. All a separable differential equation is a differential equation where all the x terms and the dx can be moved to one side, and all the y terms and the dy can be moved to the other side. That's why it's called separable. We can separate the variables, all the x's on one side, all the y's on the other, and then we can integrate both sides. If you ever see a problem that doesn't fall into that, then some other technique or possible approximation that we'll study later on in this chapter will need to be used. So the only differential equations we can solve are the ones that can be separated. So you can see in this first example, a very easy thing to do to help separate this is to move the dx to the other side by multiplying. You'll notice we have an e to the negative y on the right side with the x's, so we can of course divide that to the other side, and we've achieved a separable differential equation. I suppose before we integrate both sides and really separate it, so to speak, we should probably move that e to the negative y to the top as an e to the positive y. And now we can definitely call that a separated or a separable differential equation. Once you separate it, now we can solve it. And all that solving means is just to integrate both sides to find that original equation, or the general solution. So on the left side, the integral of e to the y with respect to y is just e to the y. Don't forget, we got to put a plus c. On the right side, the integral of sine x with respect to x is negative cosine x. And again, don't forget that plus c. To help kind of distinguish between our two different, so to speak, plus c's, I'm going to put a little subscript of 1 on the left side for that c. And I'm going to put a little subscript of 2 on the right side, plus c. So, what could we do? Well, if we were to take that c1 on the left side and subtract it to the other side, what would we get? Well, we don't know what these constants are. c2 is just some number that we don't happen to know. c1 is just some number that we don't happen to know. If we take that c1 and subtract it to the other side, we just get another constant that we don't happen to know. It's not 0, it's just another c. And that's where we're going to combine those constants of integration. I'm going to kind of lay this out in the next slide in terms of steps, but you're always going to want to put that plus c just on the right side, because ultimately you can take that plus c on the left side and move it over to the right and combine them, so to speak. So that plus c is just a combination of the c1 and the c2. It's just another constant that we don't know. Okay, so we're almost there. We need to always get y by itself. We need to solve for y when we're doing these differential equations. So we need to get that kind of e out of there. To get that e out of there, we have to do the inverse operation of e. The inverse operation of e is a natural log. So we need a natural log both sides. The key on the right side, and this would be a common mistake, is to put everything in parentheses. That natural log applies to not only the negative cosine x, but also the plus c. So we definitely need those parentheses there. When we natural log in e, they cancel each other in a manner of speaking, and we're just left with the power y. and that's our general solution. So not too bad. Somewhat like a problem we've done in the past in chapter 4, but definitely a little more difficult now that we're dealing with e's, and now we have these 2 plus c's. But luckily both of those things were not too hard to handle. Okay, so let's say we wanted to find a particular solution. Well, we would have to be given an initial condition. And the initial condition here I'm going to give you is x is equal to pi over 2 and y is equal to 2. So to find our particular solution, just like we've done since chapter 4, we need to plug in that value for x and y so we can find that constant of integration, the plus c. But here's something you might consider. When we solved for the general solution, we ended up trapping that plus c inside the natural log. So we could plug in the x and the y into the general solution at this step here, but it's probably not a good idea because that plus c is trapped. It's probably a better idea to plug it into the step where the plus c wasn't trapped inside the natural log, and that would be at the e to the y equals negative cosine x plus c. If we plug in the y of 2 and the x of pi over 2, you'll notice that we get c is equal to e squared. The cosine of pi over 2 is just 0. So our c is e squared. And now we can take that and plug it into our general solution. Y is equal to ln negative cosine x plus e squared. And that is our particular solution for that given initial condition. Just to kind of give you a visual of what's going on here, if you take this general solution and graph some of the solution curves, you'll see them here. And the particular one we have, where you can see the arrow pointing to, is that graph in green. Just to kind of give you a visual of what's going on. Okay, so here's a nice little overview of the steps you're going to always want to take. And I say always with a little hesitation because there's one special type of problem. But as long as it's not that special type of problem, which you'll see in the next slide, you'll always want to take these 5 steps here to solve a differential equation. So they're there for your reference, but I'll talk about those steps as we go through these 2 problems. So we have a differential equation here, and we have an initial condition, so we can definitely solve that differential equation. So we have to be able to separate it. And right now it's kind of stuck, so to speak. We have the x and the y in the power of e, and unless we do something to it, we really can't separate it at this point, unless you remember something. If you see a minus in the power of, in the exponent of a base, you can realize that what got you to that point was actually a division. We can rewrite e to the x minus y as e to the x over e to the y. And now it's actually really easy to separate. If we do a little cross multiplication, so to speak, we'll get e to the y times dy equals e to the x times dx. So we've achieved what we were looking for in step 1 above. We separated the variables with the y's and dy's on the left, x's and dx's on the right, and now we can integrate both sides. The integral of e to the y is e to the y. The integral of e to the x is e to the x. And just like step 3 says, we're only going to put the plus c on the right side. Step 4 is we're going to use that given point, the initial condition, to find the value of c. If we plug in 1 for y and 0 for x, we'll get e is equal to 1 plus c, and that means c is equal to e minus 1. So if we want to find our particular solution, we need to plug in that value of c. And while it doesn't look very simple, that's our value of c, e minus 1. To find y, we always need to solve for y. We would have to take a natural log of both sides in this case. Since the y is kind of trapped in the power, so to speak, we need to do the inverse of e, and that would mean take the natural log. And of course, we have to do it to both sides. So our particular solution is y equals the ln of e to the x plus e minus 1. Okay, so I think what really makes chapter 6 more difficult, so to speak, than these problems that we did back in chapter 4 is that now we've kind of lived through chapter 5 and know a bunch more integrals and What I mean by integrals is we know some other techniques or formulas for finding different integrals. So that might be what makes some of these problems a little more, if not a lot more difficult than the ones we saw back in chapter 4. Case in point is this one. But before we get to those details, we gotta first separate. You'll notice that 1 plus y squared can all be divided to the other side, and we can keep the x's on the right. The x times e to the x squared can definitely be kept on the right side, and we can move the dx also to the right side. One really important tip, I think, to keep in mind is if you have a constant, keep it on the right side with x. It's just a tip, you don't have to, but it usually makes things easier. We could have moved that 2 or divided that 2 to the other side, but it would have made this a little bit more complicated, and in some regards, if you weren't sure what to do, maybe a lot more complicated. Okay, now that we have the variables separated, we have a separable differential equation, we can integrate both sides. So this is a little more difficult than the first two examples we saw, so let's first focus on the right side. You'll notice e has stuff as a power. Almost just because of virtue of that, we would have to call that stuff, the power, u. In this case, du would be equal to 2x dx, which is fantastic. We see a 2x dx right here, and of course, if we see a 2x dx, we can replace all of that with just a du. Once we do that, the right side, pretty simple to integrate. The integral of e to the u is, of course, itself. So how do we integrate the left side? Well, you might be tempted to do u substitution. You might be tempted to call u 1 plus y squared. And that would be acceptable to at least attempt, until you realize, of course, when you figure out what du is equal to, that would be equal to 2y dy. And that's not a big deal. Of course, we could just move the 2 to the other side, divide it over as a half. But the big thing missing, and that's what makes this u substitution not work, is there is no extra y in the left side of our equation. So because of that, that is, of course, not the correct way to approach this problem. It's not a basic u substitution in that regard. So then how do we do it? Well, you'll have to recall and look back to the end of chapter 5. If you ever see the integral of du over a squared plus u squared, that was the integral for arctan. And if you need to kind of go back and look at that, I would definitely refer to that. But I'm going to kind of skip over those steps in a manner of speaking since we had that practice. So it turns out the integral of dy over 1 plus y squared is just arctan of y. And of course, like I said before, the integral of e to the u is just e to the u, and we're going to put that plus c on the right side. Okay, of course, we can plug the u back in. We don't want to leave that u there, so we have e to the x squared. We need to find y as a function of as a function of x. We've got to get the y by itself, just like in the first two examples. So we've got to get rid of arctan. In the first two examples, we needed to get rid of e, which meant we needed to do the inverse operation, which is a natural log. To get rid of arctan, we would have to take the tangent of both sides. Since tan and arctan are inverse operations of each other, they would, in a manner of speaking, cancel each other out. So if we tan arctan, those would cancel, so we're just left with y. And of course, if we tan the right side, then it would just be tan, parentheses are important, e to the x squared plus c. And again, big note to make here because sometimes the notation can throw you off if you're not fully aware of the trig notation. We cannot factor out that plus c or distribute the tan because there is technically no math involved when we're writing our trig notation. We cannot distribute, we can't multiply, we can't factor out the c, it just stays like that. And of course, if we wanted to find our particular solution, we would need some sort of point, but in this problem, we're not given a point, so that's our final answer. Okay, here we have another differential equation. We're being asked to solve it, and they give us a point so that we can find that plus c. You might want to star this example in a manner of speaking because it is a special type of differential equation. We're not going to follow exactly those steps that you saw in the last slide. It's almost the same steps, but there's one big change we need to do to get this problem to work. And to be kind of upfront about this, I think this is probably the most common kind that you'll see on the AP test. You definitely will see the other types, but I think this one might be the one that appears most often in a sense. So I don't want you to focus totally on just this one example, but just realize it's a special type that kind of needs a little adjustment to the steps that you saw from the last slide. Okay, so let's go ahead and get the first step out of the way, which is nice and easy. We're going to divide that y minus 1 to the other side, multiply the dx to the other side, and now we've separated our differential equation, which is great. Nice and easy. Okay, so on the right side, the integral of x squared, nice and easy. 1/3 x cubed plus c. Don't need to really focus much on that. But how do we integrate the left side? Well, kind of like we saw in that last example, let's at least attempt to call the bottom u and see if it works. If it works, great. If it doesn't, we'll have to adjust. So let's call the bottom u. U is equal to y minus 1, so du is equal to dy, which is great. We didn't end up with any extra y's or stuff that we don't see over in our integral, so we can definitely make this u substitution. dy becomes du, and of course the bottom we called u. What you're going to have to recall back from chapter 5 is we know this integral as a formula. The integral of du over u is the natural log of the absolute value of u. And again, the integral of x squared, nice and straightforward, 1/3 x cubed plus c. Of course, we need to take that u and plug it back in, so we're left with that as our final answer. And we have to keep those absolute values because y could be a number that would make ln negative, and we can't have a negative ln, or we can't take the natural log of a negative value. Okay, so I mentioned that this is a special problem of sorts. Two reasons, I guess. It appears a lot on the AP test, which is important, but B, it's going to require a kind of a reversal of steps that you saw from the first few examples, and that's this. If you integrate and you get an ln on the left side that traps the y, you need to first solve for y, then find the plus c. If you think about the first examples we did, we found the plus c at this point, and then we maybe solved for y or something like that. But in this particular problem, we really need to solve for y and then find that c. So how are we going to solve for y? Well, we need to do what is called an exponentiation. We need to exponentiate both sides. In other words, we need to take everything on the left and put it as a power with a base of e. We need to take everything on the right and put it as a power with a base of e. I kind of ran out of space to show maybe that little in-between step, but if you imagine an e right here with all of that as a power, the e and the ln would cancel, and we would just be left with y minus 1. And of course you can see on the right side, all of that became the power with the base of e. So maybe something you're noticing here is that the absolute values dropped off. Why is that appropriate? Why can we drop those absolute values off? Well, if you take a look at the initial condition, we're not trying to write the general solution for all the values. We know we have a point we're eventually going to plug in to find that c. And the absolute value is not needed because that y is positive 3. And if we were to plug that in, we wouldn't get a negative value. So we don't need the absolute values. Kind of makes the simplification of this a lot easier. Okay, what can we do next? Well, here's a little trick, and that's why we need to first find y, and then we can find c. This little trick is going to be used quite a bit in these problems. We need to separate the addition in the exponent, and what that means is if you ever see a operation of plus in the power of a base, we know we can separate that with the base being multiplied by each other. In one term, or one factor I should say here, it would be e to the 1/3 x cubed. In the other factor, it would be e to the c. And just imagine going backwards. If you wanted to multiply e and e, you would take the powers and add them. So we can definitely separate it. And the reason we want to separate it is for this reason. E is just a number. If we raise that number to a constant, which is just another number, we end up with another constant. So the good news is we can call e to the c just c. And that makes this much easier to deal with, because now we can just add that 1 to the other side, and that is our general solution. So we're ready to go. Once you kind of see that little trick of making e to the c just the c, and of course I'll put that in the front of the e just to make it look a little nicer, we can take that general solution, plug in our initial condition, and find the value of c. E to the 0 is 1. If I take that 1 on the right side and subtract it, we'll get 2. So c is equal to 2. And now to round out this problem, we can take the c and plug it in. So just to kind of do a quick overview of this is kind of a special problem in a sense because of the step reversal. Instead of finding plus c and then solving for y, now we're solving for y and then finding the plus c. So just keep that in mind because we'll see this type of problem quite often. Okay, a couple more examples. The only thing different with these last two examples is we're going to be asked one follow-up question. We're going to still solve these differential equations, but we're also going to need to state the domain of our solution. And there's two types of problems when we're dealing with the domain, so we'll just have to kind of keep that in mind when we're solving these differential equations that ask for a domain. So let's at least get the solving out of the way, and then we'll talk about domain. So a nice easy one to separate, we'll cross multiply, so we end up with y dy equals 4x dx. If we integrate both sides, luckily this one's a piece of cake compared to the ones we've done prior to this example. On the left side we'll have 1/2 y squared, on the right side we'll have 2x squared plus c. Again, unlike that special example you saw in the last slide, here we really should just go ahead and solve for the c. The y is not being trapped by an ln or anything like that, so I think it's a good thing just not to mess around with the algebra here. Plug in your initial condition of 2, -2 and find that value of c. It turns out the value of c in this case is -6. Now I think we can go ahead and go through the algebra here of solving for y. We need to multiply 2 to the other side, so we have 4x squared minus 12, and we're going to go ahead and take the square root of both sides, but keep in mind, anytime we take that square root, we need to put that plus minus in front of the square root. So then, is that the final answer? Is that our particular solution? Well, we have two answers here, and is one valid? Are both valid? What is the final answer here? Well, as it turns out, that initial condition is everything. Since the y value from the initial condition is negative, we only need to consider the negative answer. That's the only piece of this graph, the negative part of it, that we're using because that's where our point is. That's our initial condition. Of course, if we wanted to take into account all the solutions, then I guess we would keep both the positive and the negative answer here. But since our initial condition, the y value, from the initial condition is negative, we need to keep the equation that would give us a y value that's negative, and that would of course be the negative square root of 4x squared minus 12. So then why does this topic of domain come up in this problem? Well, if you remember back from your algebra days, when we're dealing with square root functions, domain definitely is a concern. We can never take the square root of negative numbers, so we have to ensure that the expression inside the radical has to be always positive or bigger than 0. And we just need to solve that little inequality, and that will give us the domain. If we add 12 to the other side and divide by 4, and when we take the square root, that would be our domain. X has to be bigger than the square root of 3 so that the inside of that radical is always positive. Okay, here's another example, and again we'll deal with the domain after we solve the differential equation. So as a first little step here, I'm going to go ahead and move that negative power of 2 down to the bottom with the 3 in the fraction. And then we're going to go ahead and separate. In this particular case, I'm kind of breaking a rule I said before, or a tip maybe is a more appropriate word that I said from before, where I like to leave constants on the right side. In this particular case, it just happens to work out that if I move the 3 over to the other side with the y squared, when we integrate, it works out nicely because we're going to add 1 to the power, which is 3, and divide by 3. So those 3's, of course, will reduce to be 1. But in most cases, I would still take that tip from before, where we leave the constants on the right side before we integrate. Okay, so the left side is y cubed, the integral of dx is x. And then don't forget the plus c. Again, we're not going to solve for y here, we're going to go ahead and plug in our point to find the c value, and it turns out c is equal to 0 here. To find y, or to solve y, to get it by itself, we would need to take a cubic root of both sides, so of course y equals the cubic root of x. So then why is domain important maybe in a problem like this? Well, as it turns out, if I just ask for domain for this particular function right here, I hope you would say all real numbers. If we plug in negative values for x, we can take the cubic root of negative values, so those are legal. Could we plug in 0? Well, yes, the cubic root of 0 is 0. Could we plug in positive numbers for x? Well, of course, we can take the cubic root of positive numbers. So it turns out the domain of the cubic root of x is just all real numbers. And to kind of prove that, here's a graph of the cubic root of x. It goes from negative infinity to infinity in terms of its domain. So you might be tempted to say that that's the domain, all real numbers or negative infinity to infinity. But here's kind of the key to doing this problem. Just like in that last example I did, the initial condition is kind of everything. But before I talk about the initial condition, let's define domain in terms of this problem. The domain here is the largest interval that contains that initial point, or that initial condition or value. And in this case, we're dealing with the point 1, 1. So then even now, you still might be tempted to say, well, it's still negative infinity to infinity. The dot is on the graph, and that graph goes from negative infinity to infinity. But there's one other little thing we're kind of neglecting that we wouldn't maybe realize otherwise unless we saw an example like this. And if we go back up to the original differential equation, you could realize that y cannot be equal to 0. In that derivative, the y is in the bottom, and of course we cannot divide by 0. So at our point 0, we have a hole. So this graph really doesn't go from negative infinity to infinity, it goes from negative infinity to 0, and then as a different piece, so to speak, it goes from 0 to infinity. So now we can use that definition of domain here to help us out. It's the largest interval that contains the initial value. And of the two pieces of our graph here that contains the initial condition, it of course is the right side. And we can write that domain just very simply as x is greater than 0. So two different ways to approach domain, and these will be two different things you'll want to keep in mind as you look at problems that ask you to discuss the domain of the solution to your differential equation.